Anyway, we're talking about virtual states, and I just have this this need to think in terms of make a picture in my head of what must be happening, and it's hard to do when it's an interaction like that, and it's for a microscopic thing that you can't actually see with your eyes. But I find virtual states unsatisfying as an explanation. You know, population of a virtual state and then depopulating is kind of unsatisfying because. But I think people who like to talk about virtual states, now that I realize it, I'm thinking about it as we go along here. The people who tend to talk the most about virtual states are also people who sometimes do electronically resonant cars, where we actually do populate and depopulate states. So maybe that seems like a satisfying way to them how to describe it. Yeah, maybe that. Okay, maybe I can accept that now that I think about it. Okay, PIV. Well, this is the only commercially available laser diagnostic I'll be talking about, but I want to talk about it for several reasons, including the fact that there are some new things happening with PIV, like tomographic PIV. So I wanted to show you some results from that. So that's in keeping with the afternoon's theme of scattering, things that scatter. So I want to talk about some techniques and rules of thumb. Then talk about stereoscopic PIV, and finally tomographic PIV. And some of this will be a little bit of a repeat from the introduction, so I'm going to pick up from the introduction and turn it into something bigger. So for PIV and laser Doppler anemometry, which is a single point technique, you have to seed the flow with particles, either with droplets or particles. It's really easy to make oil droplets with a nebulizer, and a lot of people use that just because it is so easy. But the oil droplets disappear when they go through a flame, and in some cases that's a good thing because then it marks the flame front. In other cases, if you actually wanted to see what happens past the flame front, it's not a good thing. So it depends on what you're seeking. The other way to do it is with ceramic particles, and those use all sorts of special little tricks to try to entrain them into the airflow. It can become very difficult. One time we did PIV in a problem, it was a project for people who were studying building fires. And those use basically buoyant forces, right? That's what drives a flame. Let's say a flame along the side of a wall of a house or something like that. That's a buoyant force. And if you start blowing particles at it, you're going to totally screw up the flow. And so getting particles like fed slowly into a buoyant flow is very difficult. It's also very difficult to get particles into a high pressure system like a gas turbine combustor rig. It's very hard to get particles at high pressure, to seed particles at high pressure into a rig like that. So that's often the hardest part of PIV. I'm going to show you some old stuff from, like I said, I think on Monday, I used to participate in the development of PIV back in the days when it was chemical film, and people thought a lot more carefully about things in those days. So your choice of particle size and the type of particle depends on how fast the flow is that you want. And this table this is from this paper here from 1997. What's the particle frequency response? How fast do you want this thing to respond? Right? So these are the two most common ceramic particles. Okay, there's their density, the gas they'd be in, okay, with viscosity and so forth. This is the frequency, the response frequency, if it's 1 kilohertz or 10 kilohertz. What diameter particle do you need? So if you're looking at 10 kilohertz, you're talking about half a micron particle. A lot of people don't use half micron particles, they use particles around 1 micron. But if you really want high frequency response, you need a small particle in order to follow the flow. If it's too big, it will have too much inertia, and it will, like if there's a vortex coming along, it'll go straight through it because it has a lot of inertia. So there's glass, olive oil, just an example of an oil. That's a little easier. Really, the oil sprays are a lot easier if you can use them. And then these micro balloons you can buy, those can be fairly big, but I don't think anybody wants to put micro balloons in a flame. So.
How do you control the flow droplet size? The injected actually the droplet size.
Yeah, the nebulizer makes that droplet size, so you have to buy one that will do that. Usually it's a medical nebulizer, but then the flow field, you can't have so much flow through it, right? That's a problem. The medical nebulizers are good at controlling size, but they don't typically have much flow in them.
So what is the outside surface of that microballoons? Like, what do they really?
What does it look like?
Yeah, what is the material of microballoons?
I'm not sure what the material is. I've never used them because they cost a lot. I've typically used ceramics myself, or oil droplets. So back in those days when we used chemical film, we had to sit and think carefully about this, how much light is going to end up at the camera, because chemical film has a particular response and you have to capture this thing very quickly. It's just going to go flash and that's it. Actually, in the old days of chemical film, if you think about it, one film was collecting both shots. And so it was in the very early days of PIV, it was not possible to do a cross correlation because both sets of images were on one film. And so you did a thing called an autocorrelation, and that had what they called a directional ambiguity. You weren't sure which direction the thing was actually moving in because it was an autocorrelation. So you had to sort of understand what was going on. And the way they separated those was to go to two-color PIV. They would use a dye laser in the red for one of the pulses and a green laser for the other pulse, and then you could use filtering to separate out the two colors and then do cross-correlation. But now you just turn up the light and turn up the camera and look at it. So I showed this before. Here's a typical system where you have two lasers. The pulses from these lasers are separated in time by some sort of delay, controllable delay. You combine them into one beam, make a sheet, go through here, and use a double image camera. The double image cameras use what's called an interline transfer architecture. The old days cameras had what they called frame transfer, where you took a whole picture in a frame and then transferred that up into a register. The interline transfer cameras took the register and turned it into stripes and put them right next to the pixel that was photosensitive. So now you just have to shift charge and dump the first image behind that vertical register, each vertical register. So in 1 microsecond, you can dump the first image into that vertical register, and then the second one is just going to have to be open, and that depends on how you shutter the camera. It's open for a long time. But you read out the first register, then you dump the second image into the register and read that out. So you can separate the two images by as little as a microsecond now. So here's a picture of a stagnation point flow flame. So there would be air flowing in this direction and fuel flowing in that direction, making a stagnation point flow flame. And then a vortex is pulsed through it. This was a study on the interaction of a vortex and a flame front, which was a this was a 1990s canonical setup for studying the interaction of a flow field with the chemistry of the flame. But you can see doing particle PIV on that thing. To get good spatial resolution, you have to seed this thing very densely. And as I said on Monday, you can't just follow the particles around. Actually, yeah, can you see it? This is actually green and red. This is from the old days. The red and green are in here, so you can separate the colors and do a cross correlation with the chemical film. So you divide this thing up into interrogation cells and you do correlations on them. So I showed you this before. These are two synthetic interrogation cells. We're going to talk a little bit about how many particles are inside each cell. You do the correlation with the FFTs, and then you get this. This is the correlation, and the offset between the center and the peak of the correlation tells you what the distance was for this thing to travel. You divide it by delta t, which is something that you set, and that gives you velocity. So it seems very straightforward. And I talked about this background noise before. There are a lot of details hiding inside commercial PIV processing software, basically. And most of the time it's just fine. But I really think it's good for you to know what's going on, which is why I thought maybe we should talk about this. In fact, I just had a disagreement with somebody a little while ago because the software is so good. Only about 40% of the vectors that were being produced were vectors that I trusted. The rest were being manufactured. And you have to be very careful because the software will just do this. And it will give you a pretty picture with lots of cool vectors. The real question is, how good are those vectors? And that is a function of what the flow field is, a lot of things. So let's talk a little bit about that. This guy, Ronald Adrian, was the person who first published a lot of stuff on PIV. And he writes really fantastic papers. He's actually the author of a book now that you can get. And maybe, have you seen that book?
Yeah.
I've never actually seen it. Is it a good book?
Yeah,
He's a fantastic author.
and lots of lot of information.
Yeah, I really admire him. He's the kind of person who just lays out all this stuff. And I'm going to lay out a little bit of that stuff. And the book comes with high recommendation. So let's talk about it. First thing he said, and this is a little bit crude, he said the imaging system is going to produce a spot corresponding to every particle. So if we assume the imaging system is diffraction limited, which is not correct, the particle size would be this, d sub I, at the chip. But it really has to do with the magnification of the system, right? So it's given by this. That's the particle image size. The magnification, that's the particle size right there. And then ds is the diffraction limited point response function of the lens. In case you haven't studied optics before, you cannot ever focus something infinite to an infinitely small spot because the lens has an outer edge to it that will cause some diffraction, and ultimately that will give you a spread in the spot at the focal spot. The best imaging you can possibly get would be a diffraction limited imaging system, but they often aren't. The problem with this whole thing is that unless you know the properties of the lens that you're using, it's very hard to get what's the real spot size. One time we analyzed a camera lens with ray tracing to try to compare it to these figures of Adrian's to try to guess how bad can it get. And it could get pretty bad, but we were using a very old lens formula that was, a design of a lens that was actually publicly available. Modern lenses are way better than that, so it's hard to say. A modern lens will not give you that image size, but this is a good way to analyze it anyway. This is the diffraction limited point response function for a lens, where that's the magnification, and this is the F number, okay? Which the F number is defined as the focal length of the lens divided by the diameter. And by diameter, with a camera lens, you can set the diameter with the aperture. It's really the aperture, the free aperture inside the lens that you're setting. So you can change the F number of a camera lens with the aperture. And then that's the wavelength of the light. So real systems are not diffraction limited. Spot size will be somewhat bigger. His spot size estimate is controlled by diffraction. They're smaller than the diameter. They're smaller if the diameter of the lens is larger, which is why it's proportional to the F number in the expression. The trouble is real lenses have aberrations, and those are not included in that estimate. Okay? And if you use a small F number, big aperture, you may suffer from aberrations. And here's why. The truth is that to focus light to a spot, say you have collimated light and you want to focus it to a spot, the index profile really should be parabolic, not spherical. And the reason it's not parabolic is that when they polish optics, they typically have a spherical surface like this. They put the optics on that spherical surface, and then they have another matched spherical surface, and there's a machine that goes around like that. Okay, and they use this polishing compound. It has a bit of ceramic grit in it, and it makes the optical surface smooth. So this thing goes. The only way you can do that is with spheres, because two spheres match each other, right? Two parabolas wouldn't do that. If you tried to take two parabolas and move this sideways, it would break. But a sphere can move back and forth and go around and polish that thing. So commercial optics are all made, except for you can get parabolic mirrors, but lenses are going to be spherical. The point is that near the center of a spherical lens, the curvature almost matches a parabola. So if you stop the lens down so that you're sampling only that part of the lens, you get very good performance. But if you open it up, you get what's called spherical aberration. The outer parts will focus longer than the inner parts, and then so you get this spread. And so it's a bit of a problem. So Adrian, in his diffraction limited spot size, says use small f number. If you do that, you could actually make the spot bigger. So you have to be a little bit careful, which is why we were analyzing this problem. Anyway, the goal is to achieve the smallest spot size possible, and so that you'll get good crisp correlations. So this estimate is still useful if you want to think about the magnification you want to use if you're going to think about a setup that you're going to set up. You don't actually have to do this because now you can just plunk stuff down and try it and see how it works. And that's what people typically do. They plunk stuff down, they look at the spot images. Well, I don't know if people even do this anymore. I'm not sure. This is what I do. I sit and stare at the spot images and try to get the absolute best quality focal spots that I can get. Sometimes, like for tomographic PIV, it's more important to have a long depth of field because you're actually now trying to sample a volume, not a plane. Okay, so you'll make the you'll use a large f number so you can get that. So it depends a little bit on what you're trying to do. In fact, this particular case I was talking about, where only 40% of the vectors were real vectors, there's a case where I think the depth of field was probably too big for the laser sheet. Okay, if you're sampling from a deep depth of field and the laser sheet is, I'm sorry, that was the other way around. Short depth of field, thick laser sheet, stuff that's outside of your sample volume, the camera sample volume, will actually still be seen by the camera, but out of focus. So if you use a depth of field that's too short with a thick laser sheet, you'll end up getting blur spots that are really huge. So you have to think a little bit about matching the sheet thickness and the depth of field of the camera. Okay, the quality of the correlation peak, the height compared to the noise, determines the error in part. And your system is automatically determining the ratio between this peak and one of the sub-peaks, right? And deciding what to think about it. And sometimes, those are called validated vectors, and sometimes, in this case I was talking about, this system automatically decides that this is no good. And then what it does is it tries to insert a vector based on averages around it. Okay, but if there's actually no good vectors for a long distance, it's going to be averaging, it's going to be inventing the gap between those, right? And that's where the problem comes in. So I typically like to look at the correlation peak and see what it looks like. And I think the software still allows you to do that if you want to. If you're starting to get something that doesn't look like it makes any sense, have a look at the correlation peaks. This is what a good correlation peak would look like. So if you start to get a lot of garbage, like for example, if you've got a couple of peaks and they're not too far away from each other and it's chosen one of those, that's garbage. I wouldn't take that. So if you start to get data that you think is a little bit questionable, stare at the correlation peaks and see how good your images really are. This is a really good test of how good is your image. Okay, if you want to get a decent quality correlation peak, you need to have over 15 particle pairs inside each interrogation cell. That need controls the spatial resolution of the flow field, because if your seeding density is low, you have to have a bigger interrogation cell. That's why people choke lots of particles through the flow field, so that they can get 15 particle pairs inside an interrogation cell. So the relative particle displacement, which is controlled by the delta t that you set the time delay between the two pulses, is also important. If the particles are too close, it'll be hard to correlate them. But if it's too big, then the second particle might have moved into the next correlation cell, right? So you have to make sure you've got the correct delta t. So the minimum in-plane displacement should be about twice the image diameter. You don't want to get any closer. You don't want the particles any closer than that to each other. Okay? And the maximum displacement should be less than 1/4 of the size of the cell. Okay, so these are just rules of thumb from Adrian. We used to sit down and calculate all this before we actually set up the film, because you can just imagine what a pain that was. You take a picture, you go to the darkroom, you develop it, you look at it, it's crap. You go take another picture. I mean, that's why we thought about this well in advance. Also, you want the image size to be about no more. This is where you get a real. This is the problem that I was having an argument about. Is that sometimes the image size was not 1/10 of the cell size. For a turbulent flow, out-of-plane motion can be a problem. Now, if you use stereoscopic PIV, out-of-plane motion isn't such a big problem. But if you're using just 2D PIV, it can be a problem. So that depends on how thick your plane is, right? When this thing starts to have a lot of out-of-plane motion, you need to make the plane thicker. And so the rule of thumb is to set W, which is the out-of-plane, if you know the out-of-plane velocity, delta 0 is the laser sheet thickness. You need to have them set that way. If there are velocity gradients inside the interrogation cell, if you did not choke this thing with a lot of particles, and now you've got a big interrogation cell, if there's a velocity gradient across the cell, it's going to smear the correlation peak, and you only see that if you look at the correlation peak. Okay? It's going to lower the height of the peak and make it difficult. It becomes more and more difficult to find the top of the peak when this thing starts to go flat like that, because there's always going to be some noise there. So these are the rules of thumb for that. Okay, you might ask, does this all really matter? I can just, set this thing up and tweak it around and make everything work. All I'm saying is if you start to get data you don't trust, these are things you should think about. There are things you can think about. Just because they sold you a thing that looks totally turnkey doesn't mean you can't sit down and think carefully about how it works. And the first thing I would do is stare at the particle images and stare at the correlation peaks and see if they make sense. Like here where I said, somewhere I said the particle image size should be no more than 0.1 of the interrogation cell size. That's actually pretty big. If you get 0.1 of the interrogation cell size, that's a very big image, and I'd start to wonder about it. Unless, I suppose, if you have really tiny interrogation cell sizes because you've got this thing so loaded with particles, you can get away with that, maybe. So that's just an introduction to the kind of issues you have to think about, especially if you're looking at challenging flows. A lot of other tricks are performed as well, and these are things that people used to publish in the literature as time went on, but now I think most of it's just hidden in the software that you use. Like, for example, so here's a particle image. When people first started doing correlations, they would correlate this cell. With its, in those days it was autocorrelation, so they would correlate it with itself. Then they would correlate this cell with itself. They don't do that anymore. They start there, then they go there, then they go there. So they overlap the cells, right? And that's a way to actually do some averaging and get some reduced noise. There are a lot of tricks for locating correlation at the subpixel level, the techniques actually come from signal processing in communications, and they work very well. So you can trust the subpixel locators, that kind of thing. Yeah, so most of you don't pay attention to what goes on inside. So why did I go on about this? I said, you know what? I sound like one of those old guys who, when I was a kid, we didn't have it so easy. But the reason I'm talking about it is that in the last 10 years, I've seen some people, they think they can just point the laser and take the pictures and then turn on the software and bang, they have a journal article. It's obvious sometimes when I look at things that the data can't be correct. So here's an example. And this is actually, I'm not going to tell you whose this was because this is somebody who interviewed for a job at the University of Edinburgh. And I challenged them about this. They ended up not getting the job. This is a spray, okay? They're doing PIV on a spray up here. Look at that. This is what you call optically thick, okay? And what that means is if we look down on the spray, say, I'll do it way over here so people over there can see it. If we're looking down on the spray, the laser sheet is going through there, okay? But this spray has a huge number of droplets in it, okay? So by optically thick, what I mean is it has an optical depth on the order of something like 6 or 7. That's getting to the point where only about, 5% of the light is actually making it out the other side. And that's because it's scattering. It's me scattering off of each drop, right? And you saw what me scattering does. It sends it in various directions, okay? So what's happening is light's coming this way, then it's hitting a drop, then it's going that way, and then it's coming out this way. So if you're trying to correlate the behavior of something inside here, then this makes no sense because it's totally displaced. Remember I was talking about you need 15 particle pairs inside an interrogation cell. Well, which interrogation cell does this belong to, right? So when something's optically thick, you're losing the signal as it comes out. So I challenged this author about that, and he said that he thought he was actually doing what they call speckle correlation. Does this? Well, you can see the speckle there. Speckle correlation is a technique they used to use in the 80s and 90s. I don't know if they still use it, but it was a way to look at the speed of, say, of a machine tool. So you just put a coherent light source like a cheap laser on the surface of a machine tool, and as it scans, you see this jittering in the speckle. If you correlate that, it'll tell you how fast it was scanning. It was a little bit like PIV. So he was saying, oh, we're just doing speckle correlation. The problem with that is, going back to this picture, speckle is caused by coherent interference. It's a coherence process, right? So it's an interference pattern. And the trouble is, you're getting interference patterns from this place. So a photon came out here. Well, maybe this one came out around. What I'm saying is that you're getting speckles from who knows what. And those things can move very rapidly. These droplets can all move very rapidly relative to each other. Okay? So even just, let's say this droplet moves a little bit in that direction, not out of the board. That's where they're trying to measure the velocity in this direction. This droplet can move a little bit in that direction, and it will totally change the speckle pattern and make it look like motion in the vertical direction. So this is nonsense, if that's the word I used before. This really is nonsense. And so the reason I brought all this up is
How does this technique to get information like external information like cone angle or penetration, not interior information?
I would never use this technique for that. You can use much simpler techniques for if you want liquid length. You can just do that with backlight imaging. How do you use this for cone angle and penetration for sprays? You can use Schlieren imaging. You can use backlight imaging. Those are all white light imaging systems that are easy to set up, not nearly as expensive, and they tell you exactly what you want to know. So I would never use them for that.
I'm just interested in knowing if the information from here would be, if I were to look at this instrument and if I were to extract that information, would it be still?
If you had this picture and you tried to get cone angle,
would it be changed because of scattering?
no more so than backlight imaging. Yeah. But you can't use this to get velocities. This makes no sense. So the reason I wanted to show you all of this is, okay, you all have to put up your hands now and promise me you will not do this. I don't ever want to see any of you presenting data like that at a conference, okay? This is just, yeah, see these nice, anytime you have a really turbulent flow and it gives you a collection of nice straight arrows, you have to ask yourself, does this make any sense? This is,
So what was the color? What was the color code?
I think that's the magnitude of the velocity, but I'm not sure.
So blue means it's greater or less?
I don't know. See, this is a case of the software made up the data for you. And so you let the software make up your data and you publish a paper. But as Professor Law said, publish quality work.
What would you do to measure the velocity at this region?
This is actually very hard to do. That's extremely hard to do. So what velocity do you actually want? Do you want the droplet velocity? Okay, you can just do phase Doppler anemometry right there, and you can get, at a single point, you can get good quality droplet velocities. And you get size distribution at the same time. Oops, I forgot to ask. The question was, sorry viewers. Any other questions? Okay. Here's a diesel spray. Oh, that's not a very good image of one. Unfortunately, I've copied that too many times. But those are extremely dense. And you're going to get as many as 10 droplet scattering events before it comes out of the spray. You just really can't correlate anything when you try to do that. Okay, let's talk about stereoscopic PIV. We're going to use...
When we do PIV, near the nozzle, the velocity is much higher than far away from the nozzle. If, for example, gas turbine nozzle. So if someone presents an image with the entire plane of the nozzle where there is high velocity and also low velocity, like that image has been taken with a fixed time scale, like time between images has been fixed. Like maybe it may not be correlated perfectly with the lower velocities.
Yeah, remember what I said before about if your speed is too high, there's a serious problem in turbulent flows doing PIV, because unless you have adaptive interrogation cells, in the old days people didn't have adaptive interrogation cells, and so there was a serious problem with a region that was really fast versus a region that was really slow, because if you're going to, you end up running into that problem with either getting the particle images too close to each other, or they exit and go into the next interrogation cell. But now the software has adaptive cells looking for, changing the size as it goes. But I honestly don't trust any PIV that's been done in the near field of a spray. It has to be done in the far field where you know that the droplet density is good enough. It's not, the droplet density should be about the same as the density that you would seed with normally. And also the droplets have to be small enough that, or either they're big so that you know you're looking at the inertia of the droplet, or they have to be small enough so you're following the gas flow. If you get in this intermediate region where they sometimes follow the flow and sometimes don't, what are you looking at, the flow or the droplet or what? I don't know. But anyway, you need to be farther down where it's less dense and it's around the same kind of density that you would use for seeding. No, there was a lot of work done in the 1980s. I mean, it's not a bad idea, but people did a lot of work in the 1980s about, can you take an image, all these different kinds of images, and can you get velocities from correlations with them? And there are lots of different ways to do image correlation with it. See, the thing about the PIV software is that is really meant to correlate point images. When you start to look at distributed structures, you have to correlate differently. I don't know if you've ever done PIV right next to a wall where the laser light just scatters off the wall. It sort of like decides that you have this intense velocity going along the wall, which is, just forget it, that's not true. But the trouble with a technique like that is that when you do Schlieren imaging, you're coming through this way, right? And Schlieren is refraction, so anytime you have an index gradient, it will start to steer light. Okay, so there might be an index gradient right here that steered some light, and then there might be an index gradient here that'll steer it that way, right? And these things can move around relative to each other. When you get an image, all these things are piled on top of each other. So what really moved, right? You don't really know, because the input face and the output face are all sort of added up together. So you can't really do image correlation velocimetry on a Schlieren image. You can do it on a shadowgram if you have a good sharp shadow image of an edge. You can do that, because now you know it's just that one feature that you're looking at, that's all. And then when it moves, you know that that feature moved. Now the problem with that is that a shadowgram is a two-dimensional representation of a three-dimensional object, and so things can move this way and you're not getting that, but you can get some motion in this direction. The other thing is that people have tried to correlate laser-induced fluorescence images. They've also tried to correlate soot emission images, and they've tried to correlate LII images. The problem with all of those techniques is that chemical reactions are going on at the same time. So let's say you're going to try to correlate soot motion. So you're going to take an incandescence image of soot. So you get this piece of soot there in your image, right? And in the next image it's down here. So you think, oh, it moved. No, chemistry could have produce more soot. So there were actually some excellent papers by Yale. Marshall Long was one of the co-authors. He's a professor there, analyzing what are the errors associated when you try to do this with laser-induced fluorescence, and it showed that you just can't do it. It's all there's just too much else going on, corrupting the quality of your velocity extraction. So you can't do it, even though it would be it would be nice if you could, but you can't. Other questions?
For this application, can you do like laser diffraction and Malvern for droplet sizing?
Can you use laser diffraction for like a Malvern for droplet sizing? You mean just to get droplet sizes?
Yeah, in the near field where it's so dense.
No, in the near field you can't. It sort of does a selective. There's a problem where it registers some sizes but not others. You have to go farther down. If you want to get near the near field to measure drop sizes, everybody complains about phase Doppler, saying you can't go into the super dense region of a spray. Well, actually, you cannot go straight into the center of the very dense region of a diesel spray with phase Doppler, but you can go closer than you can with other techniques because phase Doppler is dependent upon coherence. And the thing about a coherent signal is, even if there's lots of other noise out there, a coherent signal is recognizable. And so even if there's lots of scattering and strange things going on, if your detector sees the coherent part of the signal, even if it's weak, it will still know what that was. Whereas with some of these other techniques, it can't tell. So if you want to get droplet size near the near field, I still think phase Doppler is probably the best way to go.
The dimension of droplets you can measure with IMI.
With me?
Image means something like that.
Yeah. Yes, you can do that. In fact, there's a guy named Cyril Krua at University of Brighton who does really high resolution images at the edges of sprays and things like that. Yes, but that'll only give you what's at the very edge. Once you start to get into where there's lots of drops, you can't see. But you can do that, yeah. So compared to what you're talking about, phase Doppler could go in past that point. But actually using the two at the same time at one location would be good.
Can you really expect to see particles to follow the flow dynamics of whatever flow you're studying actually?
You can if you choose. Can you really believe that the particles are going to follow the flow? You can if you choose the correct size particles according to, for example, that table I showed. You can calculate the inertia of it, and that's actually what that paper was based on. This is a popular subject.
From the vectors generated by the software, how far can we trust the vectors near the wall? Because if they look very clear and like zero velocity near the wall, something like that, how far can we trust those?
How much can we trust the velocity vectors near a wall? What I would do is I'd open up the software and look at the correlation peaks and see if they make sense. And then I'd also, if the thing has they're going to slow down a lot, right? Which means you have to change the interrogation cell size. And so I would check the software and see if it has done that. Okay? So if everything looks good, if you have a good quality looking correlation peak and it looks like it's behaving itself in terms of things like changing the correlation cell size, then I think that's fine. Other questions? That's good. Keep it up. Okay, stereoscopic. We're going to have two cameras, and we're going to put them in this Scheimpflug arrangement. What is that? Well, really all that is a way to hold the lens. So this is the image plane in the camera. And typically, with a camera, everything is on axis. So there's an object here, and the lens is meant to map the edge of the object to the image plane. Now, if I put the camera at a strange angle, we still want to map the object to the image plane, and you just do that in this arrangement here. That's all that is. And you can buy these mounts for the camera from companies that sell this kind of stuff very easily. So basically what happens is if you do two cameras, they're looking at this flow field from different directions, okay? And so when they see something move out of plane, there's going to be a difference in the two pictures about how this thing moved out of plane. And so you can use some image processing software to figure out okay, what was in plane, in the laser plane, what was motion out of plane. And that's how you get the out of plane velocity component. So you have to do camera alignments. You have to match these things so that it can compare the two images correctly. And you do that by placing a grid in the place where the laser plane would be. And you have to match those things. And then the image processing that comes with this thing will actually extract the out of plane motion for you. So that's actually a nice setup. That's just the addition to the PIV. That's the only thing that's happening. And so it's a fairly robust way to turn PIV into. So what you're going to get is a planar image of three-dimensional velocity. So you'll get velocity vectors in the plane but also out of the plane. So here's an example from when I was in Lund. This is that I showed you before the PIV and the low swirl burner, then PIV plus PLIF and so forth. This is the same low swirl burner, but these are average velocity vectors. And the blue and the red are the out of plane components. Okay, so this is a low swirl burner. So the vectors here are for in plane velocity, and then the colors are for out of plane. You can get this kind of information very quickly, and it's robust.
So could you comment a little bit on like differences between or advantages and disadvantages between stereoscopic PIV or like using a planoptic camera instead of using optic cameras?
Can I compare stereoscopic PIV with a planoptic camera? Planoptic cameras are very cool, but for this point in time, they don't seem to have the same spatial resolution. So you can use a planoptic camera. You can even try to use a planoptic camera for tomographic. Well, it's like for tomographic techniques, for example. But for those of you who don't know, a planoptic camera is a camera that has a lens array in front of the chip. And so basically what you'll see are elements that are in and out of focus based on that lens array. And so analysis of the image sort of gives you the third dimension. But because this lens, things like the lens array and the analysis are going to set the spatial resolution of the camera, not the chip. And so they don't have the same spatial resolution as this does. Otherwise, that does also work. Other questions? But I think planoptic cameras are going to come along. They're just beginning to happen, so I think more will happen with them. So tomographic PIV. This is from, most of what I'm going to take is based on this paper here, although apparently there's a book out also. Somebody was telling me there's a book on this subject. Somebody here? Yeah.
Adrian?
Oh, really? Adrian's book does it? Okay. So you use more cameras, and they use Scheimpflug mounts as well. You can see that when you just do a stereoscopic PIV, these two cameras sit in a plane. Now you go out of plane with more cameras. And you have to align them similar to stereoscopic PIV, but more carefully, because now you have to worry about the depth as well as the plane that they sit in. So you make a thick laser sheet now. So this is not like really deep, but it's a thick laser sheet. So you get a distribution of velocities with depth. And so you have to stop down the camera lenses to give yourself a long depth of field. Now you have to use the same kind of alignment grid, but you're aligning more cameras, and you have to translate the alignment grid through the depth of the system that you're going to interrogate. So the system is going to capture 2 flow field images, in other words, like a PIV, per camera from different angles relative to the center plane of the laser sheet. So you're going to capture 4 or 5 images from different angles. So you apply a tomographic inversion on the particle pairs that are in the volume. So you basically apply a tomographic inversion on laser pulse number 1. And so what you end up is a volumetric image of particles. Then you do a tomographic inversion on the second pulse and get another volumetric image of particles, and then you correlate those. So you do 3D correlations, and you get a 3D field of velocity vectors. So here's an example from that same paper. This is they're showing every third vector, and this isosurface here is vorticity magnitude equal to this. So A here, this structure here is a Kármán vortex, and B is streamwise vortex structures. You see them there, right? That was actually a fairly slow-moving flow, but you see what you can get from tomographic PIV. So the tomographic inversion for these point images is an algebraic method versus other kinds of techniques people use for more distributed structures. It requires iterations. So you start with an assumed volumetric distribution. They call it an intensity distribution, but really it's points of light, right? So that's because we're looking at scattering from small particles. And then you try to reconstruct the signal at each pixel. So that's how you write the signal at each pixel from that distribution. So you start with this, and you multiply it by this W1, which is a weighting coefficient for each voxel. A voxel is a volumetric pixel. So you compare those, or you construct that distribution from your assumed distribution, and then you do a comparison trying to move more towards what it is you actually measured. So you have this guess at what it's supposed to look like. You have the measurement. You turn that guess into something that you compare to the measurement. It's got an error in it. You readjust the guess with this relaxation parameter mu, and you guess again. And typically this converges in 10 to 20 iterations, which surprises me. So I couldn't believe that when I first read that, but I don't do tomography, so it seems like starting out with just a uniform distribution as a guess and then converging that quickly, I think it's kind of surprising. You have to think about additional issues, and they're discussed in this paper. The quality of the reconstruction goes up with the number of cameras. So you should use 4 or 5 cameras. It's sort of, the quality kind of goes up like this and then levels out. And up here you're at 5, but you have to have at least 4 cameras. There have been some papers that a friend of mine was reviewing where they thought they were doing tomographic PIV with 2 cameras, but that's just no good. The errors are just, it's crazy. Once again, it's making up vectors. The camera should be at an angle to the plane between 15 degrees and 45 degrees. If you have very steep angles, right, you're not going to sample enough of the volume to get enough information to extract the full volume. But if you go at angles that are beyond 45 degrees, you start to make up ghost images because you're like sampling too far across this thing. You have to worry about ghost images when you do tomography. So if you use 4 or 5 cameras, you can load the flow with more particles and you get better spatial resolution. Otherwise, they can cause too many ghost particles. The calibration errors, the errors in your setup, the calibration of it should be below 0.4 per pixel, 0.4 pixels in location, I mean. But there are ways to get down to 0.1 pixel, and my colleague Brian Peterson at Edinburgh has done this in an engine, and he tells me that you can do that if you spend a lot of time and are very careful. But you have to be careful how you set it up. So you need a large depth of field, and what that means is you're not going to get the same spatial resolution as 2D PIV, although when they did the engine work, they did high-speed PIV in a plane in the center of the volumetric image, and because of the way they were doing it with the high-speed camera, they actually got better spatial resolution with the tomographic inversion. But in general, if you had like a 10 hertz system and you were doing it very, very carefully, you should get better spatial resolution with 2D PIV. So here's a picture from Brian's work where there's a volume in depth there. This is inside a piston engine. It's motored, so it's not fired, okay? And notice that the injector was up here, and he cuts off the tomographic PIV to this point because above that point, all those spray issues we discussed are happening, and so they just eliminated that data. And so what you're looking at here are velocity vectors, and these are isosurfaces of vorticity. So what they're trying to do is figure out how much vorticity does the spray impart in the in-cylinder gases when it shoots out like that, because in case you're not an engine person, turbulence is extremely important for propagation of a flame inside a cylinder. And especially for high efficiency engines, the pressure shoots up and then it shoots back down. Well, the rate what you really want is to shorten the tail when it comes back down, especially the tail on the heat release rate. You want to shorten that so that if you don't do that, then the piston will have expanded part way before you're starting to try to use this chemical energy, which means you don't have the expansion ratio that you wanted. You do not want this thing to be burning as the piston's expanding, and it's controlled in large measure by the turbulence that you impart in the engine. So it's really critical. How can the spray make this even more turbulent? So there's a paper that they've recently published some other papers on the same subject. So it's reached the point now where it's commercially available. I don't want to there's only one supplier I know of who sells this, but I don't want to be advertising for anybody. So if you need to know, maybe go to this paper. They'll actually, this guy, look him up. Anyway, we can talk about it later if you need to know. But yeah, you can even do it in a piston engine. So it's reached the point where you can do that. Can you do that in your own laboratory? I had a friend who used to work at Sandia National Labs, and he used to say, well, you just apply dollars. And you can do it. Just apply dollars. So next we'll talk about diagnostics in sprays. That was obviously an interesting subject for everybody. So we'll take a 10-minute break and come back.